All right, welcome everybody. Today we're going to talk about lesson number 90. We're going to go ahead and start our final chapter of the year, which is a chapter about limits. Now, the word limit, the idea of a limit, I have thrown that around several times this year. It's also possible that you did it a little bit last year. So while there are quite a few formulas and techniques, there's also quite a bit of common sense. Something else to keep in mind that so many of the topics that we did this year, you were expected to master, where this idea of limits, you're actually not expected to master because you are going to see it again next year. That means that while we will see some challenging problems in our lessons and homeworks, I promise that our final quiz of the year will be relatively straightforward, nothing too crazy, no open-ended questions, really just enough to make sure you understand the basic concepts. Notice here, this is homework number 90. So in your book, this is page 860 to 862. Take a look at those problems. A quick note about the last section there, 33 to 55 odd. I know that it may seem like a lot, but I promise that those are actually very quick algebraic calculations once you get to them. And then one final note that if you've been using the PDF version of the book this whole year, it's actually an older version that does not include chapter 12. I've looked for an updated copy, but there isn't one. So if you don't have a hard copy of the book to find these problems, I'm going to scan each homework page and put them in class notebook. So here in the first section, we are basically answering the most important question. What does it mean to actually be a limit? And it's basically what happens to the value of a function as x approaches the number a. So the key word here is the fact that you're approaching a number. Whether or not you can actually ever get there, whether or not the actual value of the function is defined at a, we're not actually always concerned with that. What we are concerned with is what happens to the function as you approach that number. So the first way that we're going to investigate this is by looking at a table. So in a table here, we are going to investigate the behavior of this function here, x squared minus x plus 2, and we want to do it specifically for the values of x near 2. If I'm going to ask you to evaluate a limit, I always have to give you a function, and I always have to tell you what the magic value is, which in this case is 2. So what I have here for you is I have basically the values from the graphing calculator split up for you into the values on the left-hand side here that are smaller than 2 versus the values over here in this table, which are the values that are greater than 2. We basically call that a left-handed approach and a right-handed approach. So if you take a look here, and again, these will differ by calculator in terms of how many decimal places you're going to see. But if you take a look at this left-handed side here, and you take a look at the values of x as you get closer and closer and closer and closer to 2, then you take a look at this right-handed approach, again, as you're getting smaller, but still closer and closer and closer to 2. If you were to compare these two numbers, I think you could pretty confidently say that the number between those two would be a value of 4, which is what we would say would be the limit. If you take a look over here, this is a graphical representation of what is happening to the function as the x values get closer and closer to 2. And as you can see, they're also approaching that magic value of 4. Now, obviously, it's a little bit harder to see on the graph, especially when it's on the graphing calculator, as opposed to if you had a table. The one drawback of a table, though, is that it tends to be a little bit cumbersome and it takes a little while. A little note here about using the graphing calculator. There are some examples on the homework and in the future where I will give you the table and simply ask you to analyze it. And then there are plenty of examples where you yourself will have to make the table. And if you're going to make the table, take a look at these x's. Notice that some of them are rounded to 1 decimal place. Some of them are rounded to multiple decimal places. So if you need to make a table for specific values of x, these steps over here will tell you how to do that. So this is just a little addition to the video from last year. I'm going to go ahead and show you how to actually put those steps into action on the graphing calculator. So if you go to the y equals, you would type in whatever the equation in question is, which in this case is just a nice simple polynomial. If you go ahead and press the graph, obviously it will see you'll see a picture of the graph, but again, it is sometimes difficult to determine the limit when there are no numerical values. So you can, of course, pull up the table, and if you pull up the table, you can scan through, but you'll notice here the x's go up by 1, which isn't quite enough for us to see what we want. So if you want to change that, you're going to press the second window key. That's going to bring up the table set. Here is where you can do a bunch of cool stuff. So the table start means you can start wherever you want. If we're finding the limit around 5 or around 10, you can go ahead and change it to whatever you like. Then that little delta, that means the change in table. So do you want it to go up by 1? Do you want it to go up by 0.5? Do you want it to go up by 0.1 or 0.01? You can kind of change it to whatever would be most helpful. And then actually what is the most handy thing for these limits is instead of having the auto on for the independent variable, you can go ahead and change it to the ask. If I now pull up the table, you'll see that there are no x values, which means you can plug in whatever x value you want. No need to scroll through. So in this case, since we were trying to find the limit as x got closer and closer to 2, maybe you want to plug in 1.5. Then maybe you want to plug in 1.9. Then maybe you want to plug in 1.99. So you can see what happens as you're getting closer and closer and closer to 2. So again, for these problems where you have a table, you might want to consider putting the ask in. Just another quick note here, in terms of the rounding, how your y values will be rounded, that will kind of differ from calculator to calculator. And then if you see a value that has an e, remember that that is scientific notation. So if there's a positive exponent, that indicates a really large number. And if there's a negative exponent, that indicates a really small number. Again, this just kind of summarizes what we just went over. Not only do you want to be able to tell me that as you're getting closer and closer to 2, what y value is the function approaching, but you want to be able to write it in the proper notation. So this is what we call limit notation. You use LIM for limit. You pretty much use x most of the time, although it can be a t or a y or whatever the case may be. So as x or whatever the variable is goes to whatever number was, and in this case it's 2, of the function x squared minus x plus 2, and then equal to whatever the answer is, which in this case is 4. Please note that if you don't actually know what the function is, you can simply leave this as f of x or g of x. It doesn't necessarily have to be numbers if you don't know what they are. To kind of formalize that a little bit, the definition of the limit of the function would look like this in its more general form. So the limit as x goes to some value of some function, usually f of x, but again, it could be anything, is equal to L, and that is actually the limit. And again, the point of the limit is you're getting closer and closer and closer to the value. Whether or not you actually get there, sometimes we care, sometimes we don't, but it's perfectly fine if you just get closer and closer and closer. So again, another bit of notation here is using what I just said about the fact that really when you're finding a limit, you're talking about what happens as you get closer and closer and closer, and whether or not you actually get there. Sometimes we care, sometimes we don't. So take a look at these three kind of the most famous examples. So take a look here at the first one. So if you take a look at the first one, not only are your values from the left side and the right side getting closer and closer and closer to some number, but that value actually exists. You could actually plug a into the function, get back some number, and it would actually be equal to whatever the limit L is. Compare that to the second one here. Even though as you approach the left side and as you approach the right side, you're getting closer and closer to some value. Even though the value of a is not equal to that limit, that is perfectly fine. Again, for these purposes, the limit means what value are you getting closer and closer to, even if you don't actually get there. So here, the value that you're getting close to and the value that actually exists at a are not the same, and it's fine. Finally, here in the third example, notice that the limit from the left and the limit to the right, you're getting closer and closer to some L value. Notice that because it's an open circle, that means there is no value of the function for which a actually exists. But again, we don't care about this because the limit is only asking you what y value are you getting closer and closer and closer to. So here again, we'll call this example 1, estimate the value of the limit using a table of values. So again, let's say that this was a homework problem. I would have to tell you what the function is, in this case, x minus 1 over x squared minus 1, and I would have to tell you the magic value, which in this case would be 1. What we're going to see a couple slides from now is that in a perfect world, you'd be able to just take this value and actually plug it in for each of these x's. What we're going to see here is that if we tried to do that, we're going to get 1 minus 1 over 1 minus 1, which is going to be 0 over 0. That is called the indeterminate form. And obviously 0 over 0, there's no conclusions we can draw about that, which means that just plugging the number in is not going to work. And more specifically, this is telling you to make a table. So if you were to follow those steps from the previous slide about the graphing calculator, and if you were to plug in some values of x, some of which that were less than 1, and some of which that were greater than 1, as you get closer and closer and closer to where 1 actually is, you would go ahead and make a guess that between 0.50025 and 0.499975, you could reasonably assume that between them would be 0.5 or 1/2, and then you would write your answer as a limit statement. Again, that's called the limit statement, which is that the limit as x goes to 1 of that function would be equal to, in this case, 0.5. Another example here where they want you to use a table. So again, the magic value in question is 0, and notice that they are t's instead of x's. That won't matter for your calculator. You're more than welcome to just use x's, but just know that they can be a bunch of different variables. Again, you would try, if you could, to plug the numbers in, but unfortunately, you're going to get 0 over 0. Again, that is called the indeterminate form, which means that's not going to work. So you would go ahead and type this into the y equals in your table. And I would strongly recommend that you be sure to use parentheses. They're saving a little bit of time here by showing you the positives and negatives all together. But either way, if you're approaching 0, that means you want to be a little bit above 0 and you want to be a little bit below 0. And as you see what's happening to those values of y, or f of t in this case, they're getting closer and closer and closer to 0.166666666 repeating. Hopefully, because of all your math adventures over the years, you could safely say that that is equivalent to 1/6. And then this is the limit statement right here, which says that the limit as t goes to 0 of the function is in fact equal to 1/6. So again, some of the problems will have the tables already done for you, and you just have to interpret them. And then for some of them, you have to plug them in. So you want to make sure that you do that carefully. So then what if there is no limit? And basically that means that the limit does not exist. An abbreviation for a limit that does not exist would be DNE. There are 3 different cases for which the limit does not exist. And we're going to talk about those graphically speaking, since they're a little bit harder to see just from a table. So the first way in which a limit does not exist is if there's something called a jump. And hopefully you can understand why there's a jump here, because you have to jump from one piece to the other. Basically, to summarize everything that is being said on this slide, a limit can fail to exist if the left-handed approach and the right-handed approach are not equal. So in this case, this is a famous function. It's called the Heaviside function. It's basically a piecewise function. The way that this piecewise function is defined is that it's equal to 0 for all the values that are less than 0. So that's why you get this nice horizontal line with an open circle, because you can't actually put 0 into that piece, compared to the second piece where you get a horizontal line at 1. And since you can actually put in 0, that's why you get the closed circle there. So if somebody was to ask you what is the limit as you approach 0, if you take a look at the left-hand approach, which means you're approaching 0 from the smaller values, and if you consider the right-hand approach, which means you're approaching 0 from the right hand, because those two approaches are not going to the same place, because there is a jump between those two pieces, we would say that the limit does not exist. So that's the first way in which that the limit will not exist, if the left-hand approach and the right-hand approach are going to 2 different places. The second way in which a function won't exist is if there is a function that oscillates. So oscillation means that the function goes back and forth between 2 different values. So here, they'd be asking you for the limit as x goes to 0 of the sine of pi over x. So basically, it's undefined as 0, which is why we can't just plug 0 in. So here are just a couple of values that they chose in this example: 1, 1/2, 1/3, etc. They plugged in all those values and they kept getting 0 every time. Now, again, based on the previous table examples, maybe you would say to yourself, okay, I'm getting 0, so that's probably the right answer. Anytime you have something that's kind of unfamiliar, which I think the sine of pi over x is, you really want to consider it graphically speaking. And the reason why that matters is because this is what the graph actually looks like. Turns out that for the most part, you're going to get values of y that go back and forth between -1 and positive 1, which means they keep jumping back and forth. So if they're jumping back and forth, and again, that's called oscillation or oscillating behavior, then you cannot conclude that any limit exists. So this is the second case in which there is no limit because of the fact that the function is oscillating. The third case in which the limit fails to exist is when there is a vertical asymptote. Please note that your book refers to this as unbounded behavior. So again, let's say you were going to take 1 over x squared, which is the equation for this graph right here. The magic value in question is 0. And let's say you were to plug in some x values, getting closer and closer to 0 from both the right side and the left side, the positive numbers and the negative numbers respectively. What's kind of interesting here is that as the x's get closer and closer to 0, notice that the y values are getting larger and larger and larger because they just keep getting bigger and bigger and bigger. That's why that is called unbounded behavior, because there is no bound. It just keeps going up. If it just keeps going up, up, up for now, that is classified to be a limit that does not exist. Later on in the chapter, if both sides, the left hand and the right hand, are both going the same direction, you can interpret that as a limit to infinity or a limit to negative infinity. But for now, we're going to consider it to be a limit that does not exist. So then we've been talking about limits from the right side and the left side. So there is something called a one-sided limit. And a one-sided limit basically means you only are considering one side at a time. How will you know that to be the case? Well, whatever the magic value is, if you see a little negative sign up in the superscript, you'll know that that is a left-handed limit. Whereas if you see a little plus sign up in the superscript, you know that that is a right-handed limit. So again, if you're trying to find a regular limit, meaning there is no superscript, you have to consider both sides and ensure that they both go to the same place. If you have a one-sided limit, then you're only going to try whatever side that they are telling you to, either the left side or the right side. So here, again, just kind of giving you a general example. If you are talking about, in this case, f of x, here is what the notation would look like if you're doing a left-handed approach. And here's what the notation would look like if you're doing a right-handed approach. So then kind of the big piece of that is that if you are comparing two-sided limits and one-sided limits, the only way that the whole limit can exist is if the left side limit and the right hand limit have to be equal. So if those limits are equal, then the big limit exists. If for some reason those two limits are not equal, then we would say that the limit does not exist. So let's see a couple of examples of that. And again, this is limits from a graph. So notice that in this case, they're telling you about function g. They do not give you any equations. You don't have to find them. All you have to do is be able to look at the picture. So here in part A, they are talking about the number 2. In part A, they are talking about approaching 2 from the left-hand side, hence that little negative, where then they are talking about approaching 2 from the right-hand side, hence the little positive. And then last but not least, they're talking about the full limit, which means you have to compare the two sides. So 2 is the magic number, which is here. If you're going to do the left-handed approach, you're basically going to approach 2 from the left-hand side. You can see that as you travel along that piece, the values are getting closer and closer and closer to 3. Even though there's an open circle there and you don't actually get there, we can still say with confidence that the limit approaches 3. Then if you're approaching the limit as x goes to 2, but from the right-hand side, that means you're now on this piece of the graph, getting closer and closer and closer to 2. Notice that here, even though you don't actually get there, you're getting closer and closer to 1. So this is the left-handed limit, which exists. This is the right-handed limit that exists. But because those two things are not equal, we would say that the full limit, as x just goes to regular 2, does not exist. And again, you could say DNE for short. Same graph, but part B. So now the magic number is 5. So 5 is over here. And again, we're going to consider first the left-hand approach. So if you're approaching 5 from the left-hand side, you're getting closer and closer from here, and that's going to 2. If you're approaching 5 from the right side, you're on the same piece, getting closer and closer to 2. Because the two limits are equal, you would say that the full limit as x goes to 5 is just 2. Something to notice here is that the actual f of, meaning that f of 5 if you were to actually find the equations for these graphs and plug in 5, you would get back 1 because that's where the closed circle is. So the fact that the actual value of the function is not equal to the limit, again, is fine. We're going to think about limits as just getting very, very close and not really caring about whether or not we actually get there. So a piecewise function, hopefully as you remember, you have to graph each piece over the appropriate domain. They may or may not meet, it depends. Again, there are some cases where I will give you these graphs and simply ask you to analyze them. And then there are a fair amount that you have to graph yourself and then answer. So the magic number in each of these cases is 1. First, you're going to consider it from the left side, then the right side, and then all together. So if 1 is the magic number and you're doing the left-hand approach, it's getting closer to a y value of 2. If the magic number is 1 and you're doing a right-hand approach, you're getting closer to the magic y value of 3. Because of the fact that the left-hand limit and the right-hand limit do not equal each other, that is why you would conclude that the entire limit itself does not exist. Giving you a graph here, you might want to pause and try it. So notice for this graph, I am asking you for a series of limits either from the left or right or both or just f of. So when I say f of, all I'm asking for is the function defined? Meaning, is it defined at some y value? If it is, tell me what it is. If it's not, then say undefined. So in part A, the limit as x goes to 3. So here's 3. Because it does not differentiate left side or right side, you're going to be approaching from both sides. From both sides, you can see that the y value is getting closer and closer to 0. Therefore, the limit exists at 0. When they say f of 1, what they're asking is that it at x equals 1 is the function defined. If you go down to the function when x equals 1, you're going to see that big fat open circle. Because all you see is an open circle, there is no corresponding y value. So you're going to say that the function is undefined at 1. Compare that to C, where they ask you for the limit at 1. Even though there is no actual y value that exists at 1, when you approach from the left and when you approach from the right, both of your fingers would be approaching the same y value of -5. So the limit can exist even if the actual function is undefined. That happens all the time. -2 with a plus means you're approaching -2, but from the right-hand side. So the right-hand part of the graph would be this, getting closer and closer to 4, and it matters not that it's an open circle. F of 3 means go to x equals 3, match it up with the function. Even though there isn't a full-on dot there, the function is still pretty clearly defined at -1. -2, but with the minus, means a left-handed approach. So again, -2, as you approach from the left-hand side, you're getting closer and closer to a y value of 1. In order to find the full limit at -2, you would have to consider the left-handed approach, which is here, and the right-handed approach, which is here. And because those two things are not equal, you would say the limit does not exist. And again, something to watch out for, limits do not exist. F ofs are undefined, and it is important that you kind of know that difference. F of -2, there are lots of places to look at f of -2. You're, of course, going to choose the closed circle, which is going to give you a value of 3. And then f of 4, again, even though it's not defined with an actual dot, you can still pretty definitively say that the y value is 1. Okay, so taking a look at these 4 graphs, I want you to find me the limit as x goes to 3, if it exists. And again, notice that x goes to 3, there is no left or right delineation, so you have to consider both sides and whether or not they go to the same place. So here in the first example, we can see that as you approach from the left side and as you approach from the right side, your fingers would not be going to the same place. So you would say that this limit does not exist. And again, the reason why is because of the jump. Here in the second example, as you approach 3 from the left side and as you approach 3 from the right side, even though there's an open circle here, you're getting closer and closer and closer to the same y value from both sides. So the limit does exist. You'd have to estimate, let's say it's equal to about 1/2. We'll call that B. Here in C, again, 3 is the magic number. As you approach from the left-hand side versus as you approach from the right-hand side, there the limit does not exist for a couple of reasons. One, because one arrow is going up and one arrow is going down. And secondly, again, this is what we consider unbounded behavior. The left side is getting smaller and smaller and smaller without bound. The right side is getting larger and larger without bound. But either way, we're going to consider that it does not exist. And then finally, the last one, again, the magic value is 3. I keep putting ones like this. I just want you to realize that even if there is no like big dot there, this function is pretty clearly still defined at -1. And because your finger from the left side and the right side are approaching the same value, you can confidently say that the limit does in fact equal -1. So for the homework problems tonight, if they're asking you from a graph, does the limit exist? You want to keep in mind the cases where the limit doesn't exist, if there's a jump or an oscillation or unbounded versus where they do exist, which means that even if there's an open circle, that means the limit can still exist. Finally, there are a bunch of different properties of limits, which again, you kind of have to memorize, but they're mostly common sense. Direct substitution. When I ask you to find a limit algebraically, which we're going to do for the next several days, your first hope and wish is that you're going to be able to use direct substitution, which means you're going to be able to take whatever that magic value is, and you're going to be able to just plug it into the function. If you're able to do that and you're able to get back some number, then congratulations, that's the limit. If you're not able to do that, you're going to have to do some algebraic maneuver until you can plug it in. And then even if you're not able to do that, then you have to either rely on the graph or the table. So here are a couple of the properties of limits which say, if you are finding the limit as x goes to some number of a constant, then the limit is going to be equal to just a constant. Why? Because there's nowhere to plug in the number. What if you're going to some c value for just the function x? Well, you would plug c in for x, which would give you a limit of c. In number 3, let's say you were having x to the n. Well, you would plug that value of c in for x, and that would give you a limit of c to the n. Basically, the general idea for the next couple of slides is try to plug the number in. If you can, great, that's the limit. If you can't, then you have to do something else. Bunch more limits here. This says you have 2 separate functions, one function f with a limit of L and a second function g with a limit of k. Here are 5 rules that you're allowed to say. If you know the limit of some function f and it's being multiplied by some scalar, you're allowed to just multiply whatever the limit of f is times whatever that constant is. If you know the limit of function f, and if you know the limit of function k, and you're being asked to find the sum or difference of 2 different functions, you can simply add those limits together or subtract those limits. If you're being asked to find the limit of a product, f and g, if you know the limit of f and if you know the limit of g, you can simply multiply those limits. Quotient, if you're being asked to find the quotient of f and g, you can simply divide those limits. And if you're being asked to find the limit of some function raised to a power, you can just take whatever the limit is and raise it to that power. So again, these are kind of common sense. The problems tonight are very, very straightforward. It gets harder over the next couple days, but basically your perfect world would be, can you just plug in the number? And that's called direct substitution. Basically, if you have a polynomial, which is anything with x's, you can try to plug in that magic value, and whatever you get as your y value, that's the limit. If you have a rational function, which again means variables on the top and bottom, so long as you do not get 0 on the bottom or you do not get 0 over 0, you can try to just plug in that number and simplify. That would be your limit. Oh, I guess I have the same one twice. And then finally here with a radical, if you're trying to evaluate the limit of a radical, so long as the value under the radical is positive, if it's an even root, square root, 4th root, 6th root, you're good to go. And of course it works for any value. If it's odd, cube root, 5th root, etc., then you're simply allowed to just plug it in and see what happens. So kind of showing you some very straightforward ones. And again, this is all it's going to be for tonight. Find each limit using direct substitution. That means whatever the x value is, try to plug it in and calculate it. And if you can, congratulations, that's the limit. So if you plug in 2 and you cube it, you get 8, which yes, that means that is the limit. Plug in the 4, 8 times 4. No algebraic worries there. 32 is the limit. This becomes the tangent of 3 pi over 4. Now you have to remember that 3 pi over 4 is, of course, in quadrant 2. The pi over 4 family is root 2 over 2, root 2 over 2. And in quadrant 2, they are, of course, negative. So you get a tangent of -1, but still algebraically possible. This is a polynomial, so 2 squared plus 10 plus 4. That is going to give you a value of 18. And so congratulations, that's the limit. Again, as long as there are no algebraic problems, then whatever value you get is the limit. And notice that this final problem is the same top with a new denominator. So 18 still on the top, 6 on the bottom, simplify away to be 3. So direct substitution, that is always going to be your first try for when it's algebraic. Try to see if you can just plug that number in. And again, spoiler for tonight, you're going to be able to.